Okay, today we're going to be using complex numbers and solving equations with them. So, previously when we've had an equation and we want to solve it, and we have the determinant b squared minus 4ac, and we have different situations to tell us if there's any roots, the nature of the roots of that equation. So if the discriminant is greater than 0, then we know it has two real and distinct roots. And we can call the roots alpha and beta. Yeah, beta alpha. So that's our first scenario. Now if it's equal to 0, we have two real equal roots. And so alpha and beta, where alpha equals beta. And then we have the third scenario when this is less than 0, and we say there's 0 real roots, which is true. But now we have complex numbers, so we can now enter into the imaginary plane, so we can amend this. So let's get rid of this, because we can now find a solution for such equations, where we would have two complex roots of the form x plus or minus I y. So we've got a complex conjugate pair. So we've got alpha and its complex conjugate. We'll call it alpha star. So now we can use complex numbers to always find a solution of any quadratic equation, and we'll always have two roots. Now what about higher order polynomials? So cubic and quadratic equations have real and complex roots as well. Now the degree, let's just take this note, the degree of a quadratic equation is 2, of a cubic equation is 3. So in general, the degree of any polynomial equation is the same as its highest power. So for a quadratic equation that would be 4. Now, important theorem that we're going to state, we're not going to prove it, is the fundamental theorem of algebra. And this states that a polynomial equation of degree n has n complex roots. Now, when we think about complex roots, we're basically meaning any roots. So in that we could have, remember, for x plus I, y, y might equal 0, and then we'd have a real root. So basically, with the fundamental algebra theorem, there's always going to, if the degree is n, we're going to have the degree of the polynomial is n. You're going to have n roots. So if you think about this situation, this is for a quadratic. So quadratic is n equals 2. So degree 2. We can see here, regardless of that equation, you're always going to find 2 roots. So let's do some examples. So we want to show that z equals 4 is a root of the equation z cubed minus 3z squared minus 3z minus 4 equals 0. And then we want to find all complex solutions to this. So let's let f of z equals z cubed minus 3z squared minus 3z minus 4. Now, if z equals 4, is a root, then we can put z, the f of 4 is going to be 4 cubed minus 3 times 4 squared minus 3 times 4 minus 4. So if this is a root, this should now equal 0. So if you chug this into your calculator, you will indeed find that all that works out at 0. Therefore, z equals 4 is a root. So if z equals 4 is a root, then we can say that z minus 4 is a factor. So that means z minus 4 multiplied, now we've taken a z out, so the highest, so the rest of this is going to be, the highest degree is going to be z squared, sorry, plus z, but we don't know the coefficient of z, so we're going to call it a, and then plus, now what number here? 4 is the root, and 4 here. So if you when you think about if you multiply out the brackets here, you're going to be coming back to this. So 4 times whatever number goes here must equal minus 4. Whichever number is here must equal minus 4. So it's going to be plus 1. Now let's open up the brackets, and we're going to do each. So we'll do the z's first. So z times z squared is going to be z cubed. Z times az is going to be plus az squared. Z times 1 is just plus z. Now we're going to do the minus 4 part, but we're going to do it so and we're going to put it under here. So minus 4 times, and then we're going to line up the terms are the same. So minus 4 times z squared is going to be minus 4 az squared. Oh, sorry, no, it's not. Minus 4 is going to be minus 4 z squared. Then minus 4 times az is going to be minus 4 4a z, and then minus 4 times 1 is just going to be minus 4. Now we can add them, to get these two bits together. So we're going to have the z cubed, then we're going to have plus a minus 4 z squared, then plus 1 minus 4a z, then minus 4. Now we can compare coefficients. So we're going to compare coefficients. So here z squared is minus 3. So we've got minus 3 must equal a minus 4, and minus 3 must equal 1 minus 4a. So we can work out here that a is going to be equal to 1. And if we check this out here, a equals 1 equals minus 3 equals 1 minus 4, which is correct. So now we can substitute the a into this. So we've got z minus 4 z squared plus z plus 1 equals 0. Now we can solve this part here. So we're going to solve z squared plus z plus 1 equals 0, and we'll use our quadratic formula. So it's going to be minus 1 plus or minus square root of 1 squared minus 4 times 1 all over 2. So this will work out minus 1 plus or minus square root of minus 3 all over 2. So we can now, z is going to be equal to minus 1 plus or minus I root 3 over 2. So we've got a degree 3 polynomial, and we've got 3 roots. Z equals 4 and z equals minus 1 plus or minus I root 3, 2. And because we've got z in its complex conjugate, that is the answer. Okay, so when a polynomial equation with real coefficients has complex roots, they occur in conjugate pairs. So with these polynomials, when we're finding the roots, you're going to be looking for conjugate pairs. Now with a cubic equation, which we just looked at, has 3 roots because of the fundamental theorem of algebra. And we can write it as a linear factor and a quadratic factor. Now that's just exactly what we did in our example. So let's look back and see how we did that. So when we came to here, here's our linear factor and here's our quadratic factor. So when you've got a cubic polynomial, you can always write it as the linear and the quadratic factors multiplied together. Therefore, a cubic equation must always have at least one real root. So they either have, so cubics either have 3 real roots, that's a possibility, and you've solved those kinds of equations before, so they can have 3 real roots, or 1 real root and 2 complex roots of the form x plus or minus I y. So the complex conjugate pair. Now, a new sheet up actually. But let's think about a quadratic equation. So that's a degree 4. So it has 4 roots because of the fundamental theorem of algebra. And these can either be 4 real roots, or they can have 2 real roots and 2 complex roots of the form x plus or minus iy, so the complex conjugate pair, or they can have 4 complex roots. So you would have x plus or minus iy and say a plus or minus ib. So that you'd have, i.e., 2 sets of complex conjugate pairs. A quadratic can never have 1 real and 3 complex roots. And if you think about it, it's because you always need to, the complex roots always come in a complex conjugate pair. So you can have 2 complex roots or 4 complex roots, but if you had 3 roots, then one wouldn't have its complex conjugate pair. So that's why you always need to have the roots with the complex conjugate pair. Okay, let's do another example. So z minus 2i is a factor of the equation z to the power 4 plus 13z squared plus 36 equals 0. So I want to solve the equation. So if, since z minus 2i is a factor, z plus 2i is a factor. Now, if we take z minus 2i and multiply z plus 2i, we're going to get z squared plus 2iz minus 2iz, so they'll cancel out, minus 4i squared, which comes out at z squared plus 4. Now the reason we do this is we can now take this and we can rewrite our quadratic equation. What's meant to be 13? And that's going to equal, so we can take our, so these are two factors that we've just multiplied together, so we can do right like that, and then we can do, we can now write a quadratic equation. Z squared plus k, we don't know what the coefficient for the z part is. Now, we've got 4 here. 4 needs to multiply with the number we're going to put here to give us 36. So 36 divided by 4 is 9. So 4 times 9 gives us the 36. So that's how you choose the number that's going to come here. So now let's do what we did previously, and we'll go through, we'll multiply through with the z squared. So we'll get z to power 4. Then we'll have plus k z cubed plus 9z squared. Now we're going to have 4 multiplied by z squared, so that's going to come over here. Um, 4z squared, then 4 multiplied by k plus 4kz, and then 9 plus 36. And now we will add them together. So we're going to have z to the power 4 plus kz cubed plus 13k squared plus 4kz plus 36. Now, comparing coefficients, so if you look here, there's no z cubed and there's no z factors, therefore k must equal 0. So that gives us z to the power 4 plus 13z squared plus 36 must equal z squared plus 4, then z squared plus 9 equals 0. So now we can take this z is going to equal, so z squared equals minus 4 and z squared equals minus 9. So z must equal plus or minus 2i and z must equal plus or minus the square root of minus 9, which is equal to plus or minus 3i. So this is what we have up here already, what we worked out here, and this is the other roots. So our roots are z equals plus or minus 2i and z equals plus or minus 3i. So here we've got 4 complex roots. Okay, now we're going to find the square roots of a complex number. Okay, so let's do this with an example. So we want to find the square roots of -2 minus 2 root 3 I and show their position on an R-gram diagram. So we want to find the roots so that they're going to be of the form x plus I y. So x plus I y must equal plus or minus -2 minus 2 root 3 I. So that's the square root of this. But what we're going to do is square this side so we get rid of the square root. And we're going to multiply this out. So we'll do x plus iy, x plus iy, which will give us x squared plus xyi plus I squared y squared, which I squared is going to be, so it's going to be x squared, but I squared is going to be -1, so it's going to be minus y squared plus 2yi. Was meant to be an x in there too. An x in there too. So what we've got here is we've got a real part and we've got an imaginary part. So x squared minus y squared plus 2xyi must equal -2 minus 2 root 3 I. But here we've got a real part and we've got an imaginary part. So x squared minus y squared must equal -2, and 2xy must equal -2 root 3. So here we can find x is going to be equal to y, sorry, we find y here. Y is going to be equal to root 3 over 2. I will just deal with that bit there. Substituting that back into here, and that gives us x squared minus root 3 over 2 squared equals -2. So x squared equals 3 over, oh that's not 2, that's meant to be, oh dear. So here, 2's cancel and the x comes down here. So that's going to be slow down. minus x squared equals minus 2. Now we want to get rid of this, so we're going to multiply through by x squared. So it's going to be x to the power 4 minus 3 equals minus 2x squared. And so we're going to turn this, we're going to bring this over, x to the power 4 plus 2x squared minus 3 equals 0. Now, this looks a little bit like a quadratic equation, but it's a quadratic equation, but we're going to use a substitution. So let's let u equal x squared. So now we have u squared plus 2u minus 3 equals 0, and we can solve this. So u equals u plus 3, u minus 1 equals 0, so u is going to be minus 3, or u is going to be 1, but this is x squared equals minus 3, and x squared equals 1. Now, we're finding the value of x, and x is a real number. So we're going to not regard this one because it's going to give us an imaginary number. So x must be equal to plus or minus 1. So I'm going to write it up here. So x equals plus or minus 1, and y is going to equal root is root 3 over x, so it's going to end up being plus or minus root 3. So our roots are going to be, so the square root of minus 2 minus 2 root 3i is going to be plus 1 plus I root 3, or minus 1 minus I root 3. So if we draw these on the Argand diagram, 1 root 3 will be about here, so 1 root 3, and then we've got minus root 3 minus 1, so down here. Okay. Now we're going to look at an interesting result for cube roots of 1. So let's consider z cubed minus 1 equals 0. So because of the fundamental theorem of algebra, this has 3 roots. So z must equal 3 root, the cube root of 1. And that equals 1 is the real solution. However, there must be 2 complex roots where x is plus or minus iy. So because we've got z cubed minus 1 must equal z minus 1, then have z squared plus k z plus 1. And now we can multiply that through, so we'll have z cubed plus kz squared plus z. Then we do the minus 1, so we'll have minus z squared this one, minus kz, and then minus 1. So that gives us z cubed plus k minus 1 z squared plus 1 minus k z minus 1. So equating coefficients, k minus 1 must equal 0, so k equals 1. And that works for both parts here. So therefore we have z cubed minus 1 equals z minus 1 z squared plus z plus 1. And now we can solve this bit using the quadratic formula. So z is going to be equal to minus 1 plus or minus 1 squared minus 4, 1 over 2, which comes out at minus 1 plus or minus root 3, minus 3 over 2. So we have z equals 1 is a root, and we have z equals minus 1 plus I root 3 over 2, and we have z equals minus 1 minus I root 3 over 2. Now these results are really helpful when we want to deal with anything that is a cube root. And we're going to do an example to show why. So let's solve z cubed equals 8. Now, this is a degree 3 polynomial. Therefore, there's 3 solutions. We know that z is going to be equal to the cube root of 8, which is 2. There's a real solution. But there must be 2 complex solutions. So we can take the cube root of 1, which is 1, and multiply it by 2. But we already know what the cube root of 1 is, because we've just done it. It's these. So we can take, so we know that z's going to be, those were z equals 1. The cube root of 1 is going to be 1 or minus 1 plus I root 3 over 2 or minus 1 minus I root 3 over 2. So we can now take, we're going to have 2 or 2 times minus 1 plus I root 3 over 2 or 2 times minus 1 minus I root 3 over 2. So that just gives us 2 or minus 1 plus I root 3 or minus 1 minus I root 3. These are the 3 solutions. So I hope that helps.